All right. First of all, okay, I'm introduced already. Thank you. So thanks very much to the organizers for organizing such a big meeting and for the invitation. So I have a short talk today. This is a talk, as the title indicates, about ADS-CFT, and the aim is to discuss first some conformal theories that then undergo confinement and screening using holography. Right? So the plan is first to define a good UV fixed point, to discuss an infinite family of n equals 2 conformal theories in 4 dimensions, then break conformality in a way that will lead to a gap system preserving less supersymmetry. And I will focus on one of the many possible examples that one can do of this. There are many technical aspects. I will try to focus mostly on the ideas, taking out technical details. And this talk is based on work with PhD students, postdocs, and faculties in different combinations in the last 6-7 months. Ali Fatemi and Peter Weck are in the audience. Okay, so let's go with it. Let me first start by reminding, and this is mostly for the young people in the audience, just very flash one transparency about things that were done 20 years ago. So the idea is that, and by the way, there are lots of interesting references here who have done very interesting work. I will mention none of them. There were different ways of construct holographic duals to field theories like Young-Mills or QCD-like theories and supersymmetric versions of them. One of the ideas was this one I'm trying to draw here, to start with n equals 4, deformed by a relevant or a bed, and ending in some flow. Typically, it was happening that the end of the flow was singular. Then another idea was to start with a 2-node quiver and making a quasi-marginal deformation, following the full flow up to the IR. And another idea was to start studying higher dimensional branes, wrapping them on some compact cycles, studying supersymmetric theories in 3+1, 2+1, and 1+1 with different amounts of SUSY. All these gravity duals had, one way or another, some problems. Okay, so the ones I'm mentioning here is that if the UV was well defined, like in the first class of duals, then the infrared was typically singular. In cases in which the infrared was well defined, the UV was not strictly asymptotically ADS, and in other cases, the ones of wrapped branes, the UV was non-field theoretical. This was difficult in a lot, the application of holographic normalization. Another feature of these systems is that the addition of a large number, by which I mean NF similar to NC, of quarks or matter transforming in the fundamental was technically very challenging, and it had effects, not nice effects, both in the UV and in the IR of these geometries. Okay? So aside from this, all these negative points I mentioned, there were numerous things that when were calculated using these systems, they gave very nice results, and people learned many things here. So the question in this talk is if it would be possible to keep the virtues of these systems, namely a well-defined IR, repair the UV, making it asymptotical ADS, and also add localized sources. Okay, so this is what I'll try to discuss, how to do this in one example. So the idea is how to fix the issues I was mentioning, keeping the virtues. And the idea will be to start with a CFT, actually with a family of CFTs, that contains fields in the adjoint, in the bifundamental, and in the fundamental representations, deform this by a web, okay? These are UV fixed points, well-defined UV fixed points, deform them by a web, and to preserve SUSY, make a mixing, a twisting between their symmetry and the Lorentz group. So the idea is represented here. We will have a D+1 superconformal theory with some R symmetry. We are going to compactify on a circle the D+1 conformal theory, breaking conformality, but in order to preserve some SUSY, we'll need to make some mixing between the R symmetry and the Lorentz group. Okay? So there we go. So let me start by defining, that was the idea, let me start by defining the UV fixed points I will be working with. Okay, so for I chose for this talk, because maybe it's a language that we all share, to work with n equals 2 4-dimensional conformal theories. Okay? So the type of theories, and here is the price you pay, are quiver-like theories like this one, gauge group SUN1, SUN2 up to SUNP, flavor groups F1, SUF1, SUF2 up to SUFP. The field theories, if they are conformal, they have these global symmetries, the conformal group in 4D, SU2 cross U1, that's the R symmetry of n equals 2 theories. And one thing that I remind you is that these particular theories, this is a Hanani-Witten setup. For those of you who are familiar with them, might illuminate something, but I will not use it. For these particular theories, the beta function is one loop exact, and is given by twice the number of colors minus the number of flavors, which means in this context that for this theory to be conformal, one needs to ensure, for example, that twice n1 is f1 plus n2, 2n2 is n1 plus n3 plus f2, and all these equalities that are listed there. Okay? So one nice way to encode this information in one function, all this kinematical information in one function, and it's very useful for the holographic picture, is the following. One can define a function that I will refer to it as rank function. It's a function that in terms of a variable x, at x equals 0 is 0, and at x equals p plus 1, p is the number of color groups of the system, is also going to be 0. And notice this, at x equals 1 is n1, at x equals 2 is n2, and it's a polygonal, as I wrote there, right? It's a convex polygonal, right? So the next slope is always smaller than the previous, right? So it's always closing like this. If you calculate the derivative of this function, you will find this here. So you see it's a discontinuous function. And if you calculate the second derivative, you will have a sequence of deltas at the different points. And so the thing to observe here is that this function is encoding the quiver we had in the previous slide, the numbers n1, n2, etc., up to np, and the numbers f1 up to fp, in the following way. The rank function evaluated at the integer values gives you n1, n2, etc., all the gauge nodes, and the second derivative contains as coefficients of the deltas the number of flavors. Okay, so this is a tool that is quite useful to discuss the holographic dual. That is what I'm going to do now. Okay, so the holographic dual was discussed in two papers, basically, where they set the problem and then resolve it. The first paper is a paper by Lin, Lunin, and Maldacen of 2005, and the second is by Gayotto and Maldacen in 2010. They presented things in M-theory. I'm going to tell you what the type 2A version of this is. So the idea is the following. They are searching for holographic duals to conformal theories in 4 dimensions, so they need to write an ADS5. The field theories must have n equals 2 supersymmetry, so they need to have SU2 times U1. The SU2 geometrically they are representing with these two spheres, and the U1 with that circle. Notice that there are 2 extra remaining coordinates. All these work factors here from F1 to F8, they can only depend on these coordinates, otherwise they would break the isometries. And notice that all the Ramon and Neves-Schwarz fields, they are consistent with these symmetries. So what these authors here did was to write these BPS equations. This system ran the BPS equations for the system, and this leads you into a system of first order, nonlinear, uncoupled BPS equations for F1 up to F8, right? So it's quite a difficult problem to solve, but it happens that if you start operating with these partial differential equations, you are able to solve algebraically almost for all the functions F1 to F8 in terms of a given function. I will refer to it as potential and its derivatives respect to sigma and eta. So this is an expression for the first function, that's an expression for the second, etc., etc. This continues like this. So what's interesting is that this very complicated problem boils into a very simple problem for the function b that solves a Laplace-like equation with certain given boundary conditions to ensure the health of the system. So that's the Laplace-like equation, so it's a linear equation, and some boundary conditions. And what's most interesting is that this rank function we were defining before enters as sort of an initial condition for the Laplace problem, okay? So you can take this system, choose a given rank function, and separate variables and solve it. That's the solution. So you see it's kind of a Fourier Bessel series where the Fourier coefficients are the Fourier transform of the rank function. So the way you think about this problem is the following. First, you choose your conformal theory. You make sure that satisfies this numerology. Then, then you come to this slide and you write the potential where the coefficients, these coefficients are in terms of the rank function you wrote to represent this field theory. With this potential, you come back here, you put it in these functions, and then you put it in the background, and that's your holographic dual. Okay, so that's the idea of these holographic duals. And just let me say, and I'm not going to go into this, that there are many checks that these supergravity backgrounds capture aspects, non-perturbative and perturbative aspects of these quantum field theories, of these conformal theories. That's a list of some of those aspects. And these calculations have been done both in holography and also in taking the field theory, doing localization, and with the matrix model, okay? So, and this type of logic I was describing here can be extended for superconformal theories in different dimensions. Let me not go there. So what I want to discuss now is how to use this family of 4D n equals 2 conformal theories in order to leave the conformal world and going into something that is going to end up in a gap theory. Okay? So the idea is something that many of you are very familiar with. Field theoretically, you use that conformal theory as a UV fixed point, you deform by a web or by a relevant, you flow into some interesting dynamics, typically strongly coupled. Holographically, what you do is, and this is what I'm going to show you how to do very, very briefly, is associate this CFT with the backgrounds like the ones I was discussing before, but then make a deformation in the background by either adding some Ramon or some Neves-Schwarz fields. This produces a deformation of the ADS and the internal space. There is a flow into some infrared geometry that we will impose is smooth. Okay, so the whole system will be trustable at the level of supergravity, and the proposal will be that all this flow is representing all this flow. Okay, so how to do this explicitly in an example that can more or less be understood? The idea is the following. We are going to take metrics, in particular applied to the system I was discussing before. We are going to take metrics that for large values of R are going to be ADS times some internal space, and I'm going to be thinking about the ones I discussed before. In general, what will happen is that this function here, that is the same as this one, will have this form. So you can see that at R going to infinity, this is a 1, so that's ADS. And this function here will have this form. So what's happening here is that one is taking the conformal theory, wrapping it on a circle that's indicated here by the angle phi, and imposing some work factor here and there. At the same time, one is mixing the R symmetry, in this case a particular U1 of the R symmetry, with that direction, and that will preserve supersymmetry. Okay? So this type of things is very much inspired, and I'm going to show you a particular example now, in a very nice paper by Andrés Anabalón and Simon Ross in 2021, very nicely studied in the case of n equals 4 by Prem, Kumar, and Ricardo Stuardo. So once again, the idea is take a CFT, wrap it on a circle, mix it with the R symmetry so that supersymmetry is preserved, and go along the flow and end up in a quantum field theory in one dimension less with the same similar structure of R symmetry. So what I'll show you now, okay, so this is once again what's happening in the quantum field theory. There is a UV CFT with an R symmetry. One is picking a U1 inside that R symmetry and mixing it with the circle direction on which we compactify the field theory. the background is smooth all along the flow, and thanks to this mixing, this twisting, one can preserve some amount of SUSY. The gravity background indicates a transition between a CFT and a quantum field theory in one dimension less that is gapped. Okay? And one can play this trick in different scenarios. I will show you this trick play in the n equals 2 for these theories that I was discussing before. So let me briefly go there. This is how the background looks like. So let me tell you a bit of what's here. These functions, f1, f2, f4, etc., they are the same ones as in the original CFT. Okay, so these ones with the tilde will not change. Notice that what changed is the ADS5 that now is given by this. Once again, what we are doing is taking one direction, periodically identifying it, and putting a work factor in front. And notice that the theory, the original theory, had an SU2 cross U1 R symmetry. Both are mixed with this phi direction in order for this to work nicely. Okay? There are also some Ramon and Neve-Schwarz fields that capture what's needed for this to be a solution of the equations of motion. Okay? So what we are doing then is a twist compactification on a 4D n equals 2 linear quiver to 3 dimensions in this case, preserving 4 supersymmetries, leading to a gap system at low energies. Okay? So, what can we calculate with these backgrounds? So, analyzing the asymptotics, notice this is asymptotic LADS, so using holographic normalization is safe. One can see that depending on the parameters of the solution, one can have SUSY breaking if this parameter mu is non-zero. I'm going to take it 0. Or also a bed for a component of the R symmetry current. Okay? Is this bed the one that triggers the flow in our case? So this is quite universal and happens in all this infinite family of backgrounds. You can also calculate Wilson loops doing the usual thing, namely proposing a string configuration, separating the ends of the string, letting the string penetrate into the bulk, and then measuring the energy, measuring in terms of the separation, and finding that at low separations, so in the UV, the theory is conformal, so the energy is 1 over L, whilst as I increase the separation, the energy goes proportional to the separation, right? So it's a confining theory. I will have more comments about this in a moment. Other things that can be calculated, and don't pay much attention here to the formulas, this is a C function, a function that, following the question that was asked before, should measure the number of degrees of freedom as we move in the radial direction. So it's basically, the formula looks a bit complicated, but the bottom line, the idea here, is that this is measuring the volume of the internal space, or, if you wish, is measuring the inverse of the Newton constant if you were to reduce the theory to 5 dimensions. So, okay, there is a complicated formula, it's not that important, but using the functions in these backgrounds, what you notice is a universal behavior, and what you observe is that for these systems on which there is a flow across dimensions, the system goes from 4-dimensional in the UV to 3-dimensional in the IR, the number of degrees of freedom measured by this quantity goes to 0 far in the IR, indicating that the system is gapped, and then goes to a constant that is the same constant that one associates with the number of degrees of freedom for each one of the members, or any one of the members of this family of conformal theories. So there is something quite universal here, that is that this quantity and many others basically break up into a quantity that refers to the UV CFT and a quantity that refers to the flow. Okay? And this phenomenology happens for many other observables. And I'm indicating here some of them, the entanglement, entropy, the complexity, but there are some others. Okay? These universal behaviors are actually a consequence of a development a long time ago by Gauntlet and Varela, and this universality is very non-trivial from the viewpoint of the quantum field theory. In holography is almost a trivial consequence of this development of Gauntlet and Varela. I want to emphasize that flow central charge is monotonic it detects the UV conformal point, it detects the gap IR, and it's a flow across dimensions. So this is something that is kind of difficult to define field theoretically. One can calculate other things, and I emphasize on certain universalities, so things that are the same or the same behavior for the different members of the family, infinite family of conformal theories. So to close this, let me briefly comment on something in progress with Ali Fatemi and Mauro Giliberti that is strictly non-universal. Okay? So the thing is how to understand the phenomenon of screening in these theories. Okay? So in these systems we have color groups and flavor groups. Why did the Wilson loop I was presenting before did show a confining result, given that whenever you have flavors, you could have in principle screening? Okay? The trick here is that the string probe we were using in the beginning for the Wilson loop is allowed to move in the radial direction, giving the usual Wilson loop, whilst the string also wants to move in the direction of the quiver. Let me call it eta here. It's one of these directions in the gravity background. So if you allow the string to move both in the radial direction, the usual Wilson loop, and in the quiver direction, you have a more complicated action. You still have a conserved Hamiltonian, but it's not enough to solve completely the problem. So the result I'm going to show you now was done in a system that is quite similar to the one I was discussing up to now. There are some technical differences, but it's the one that we are making work with Ali Fatemi Bari and Mauro Giliberti. So the idea is that putting this probe fundamental string into the bulk and allowing to explore the radial direction and explore the quiver direction, one finds that the fundamental string wants to dive into the flavor group. So wants to move in the quiver direction and attach to the flavor group. So this is a form of screening, and it's very non-universal because it depends where the flavor group is, etc., etc. So in the next page, to close this, I'll show you some plots, and there are still many various things to understand and explore about this. So let me show you some plots. We are doing this in these plots, can be done for many different examples and have been done for many different examples. For this particular quiver, we are taking, say, the first color group. We are putting there a heavy quark and anti-quark in the prescription of Wilson, and we are letting a string explore the whole bulk. Okay? So what's happening, if you look here, is that one finds for the energy in terms of the separation a law that is first conformal, indicating that for small separations the system is almost a conformal theory in the far UV, then goes into a confining regime, okay, kind of linear, and then asymptotically goes into a constant energy, indicating screening. This is a plot of the strings in the direction of the quiver, just for you to see that they actually want to go to the position of the flavor group that here is there. So we have found in this example and in many other different examples that the energy in terms of separation always follows a law of this type, something that looks like a conformal law, and then something that when you expand at small separations or longer separations gives you first confinement and then screening. Okay? So let me close this with some conclusions, some comments. I have presented one example, so an infinite family of examples in 4-dimensional n=2 conformal theories of a formalism to construct holographic duals to these systems with 8 Poincaré supersymmetries. This can be generalized to all the possible dimensions where this type of formalism can be generalized to all the possible dimensions where there is a conformality and supersymmetry coexisting. I have shown how to use these conformal theories as a UV fixed point for an RG flow, ending in a gap field theory, and it's also possible, these are different solutions I didn't discuss today, to end in another fixed point. Okay? Many observables can be calculated in the conformal theory. They are quite interesting along the flow. Some are universal, some are not. And it's interesting to better understand how the dynamics induced by these flavor groups, like the ones I had before, are influencing the dynamics. I'm presently exploring similar situations with or without SUSY, calculating correlation functions and other observables. With this, I wanted to finish. Thanks very much for your attention. David.
Yeah, just two quick questions. The first one is, can you separate the scale from the infrared gap, from the scale where the lower dimensional theory, which is confining, becomes higher dimensional?
No. As usual, right? This, I think, is going to be a feature of all these models. Put it in different words. The Kaluza-Klein modes of the reduction of the circle will have the same value as the confinement scale, as the Young-Mills scale, say.
Thanks. And the second one is, you talked about screening, but can you actually see string breaking here?
No. Very good. This we discussed very well in the paper. What we are seeing, very correct, right, your point. What we are seeing is that the string wants to go to the flavor group, right? Now there, another phenomena has to take place that is not in our ansatz, this one, okay? The phenomena is the phenomena of the string disconnecting and connecting to the brain. Now, notice this. There are NF flavor brains, there are NC colors, and when you look, they are commensurate. So NF over NC is order 1, so the diagram is not suppressed as it was in the past, etc., right? That argument that was given. But the answer to your question that is correct is, no, we do not see here with this thing the string breaking, right? That's not contained in here.
Okay, we can.
Okay, yeah, we can talk if you want. Yeah.
I'm confused by your use of the Nambu-Goto action for the description of the string. Don't you have a B field and a dilaton as well?
Show me a bit higher.
Don't you need to incorporate the dilaton and the B field as well in the action for the string?
Not for the Nambu-Goto. If I were dealing with the D1 or etc., that would be the Born-Infeld action. Okay, you disagree, then we can talk. Okay.
If there are no more questions,
thanks very much.
Thank you very much, Carlos.